Tonight I need to be up to study for my 2 exams. Gotta get some sleep. Again.
I will try to find it. You might, yeah. This is.
All right, so today we're going to do a review for exam 2 on Friday. Announcements, homework 7 is due. It's the last homework assignment. That's fantastic. On Friday, and we'll release the data sheet on Wednesday. Office hours are today. Then presentations start next week. Your attendance is required. You have to actually grade each other's talks. And then I'll reach out to the 4 that are going on Monday. We'll arrange special office hours. And then I don't know if it's up yet, but the rest of you will have through a spreadsheet online where you can sign up for practice sessions with me or James or Matt. And then, so let's see, we are just about here. We're here. And then after this is student presentations. And basically all you're doing in lab is your projects. You'll be milestone meetings. We'll have a guest speaker on Wednesday. I still think that's true. I think you just confirmed. All right, any logistics questions? Yeah.
Before it was just 1670, we have both rooms.
Oh.
A 1670, like on the slides it was.
Should be just 1670. Where do you see that?
Like on the previous slide.
Okay.
Yeah.
Okay, that's great. Any other questions? All right, so we'll do a review. This is your chance to ask me questions. I can blast through these slides real fast. We can get out of here, but then you won't learn anything. So, logistics. Oh, presentation. We don't need that. Midterm logistics. That date's wrong. No, it's still right. Number of rooms is wrong. So closed notes, closed books. You can bring whatever calculator you want because it used to be just scientific and 4 function because you could have a calculator that could actually run probably run Armed Core Force anyways. And you could probably have an emulator on there, but then we figured nobody actually has these calculators anymore. Everybody has graphing calculators, and what am I going to do? Then we get lots of people asking if they can bring their special calculator in. I don't care, just don't run emulators on it or have extra notes and all that other stuff. All right.
Store them. Of course.
And then no phones and other devices, and we'll make sure there's a timer fate on the screen this time and not just the one in the back of the room. Any other logistics questions? Okay. Same thing as last time. Don't spend too much time on any one problem. You're welcome to start a design problem first if you would like. See all your assumptions. It's much easier. You can get so much extra credit if you just say, this is what I'm trying to do, especially for the last couple questions of the design problem where you're like rushing anyways. You can just say, this is what it's supposed to do. Just write it in text. Great. You're not going to get all the points, but you'll get some points. At least we have something to grade. Just leaving it blank gives you 0 opportunity to give any points. All right, and that's back to partial credit is rare if you don't show your work. So if you at least write something, I can grade it. Data sheets are made available, and we'll post any. You can ask questions on Piazza. I don't know, this year, either our data sheets are really good or you guys aren't asking questions. Usually we have a lot more questions, but if you have questions about the data sheet or there's errors in it, please let us know. And we'll announce any of the changes on Piazza. All right, so what to study? Homeworks, labs, old midterms have been on the site for about a month. You're going to be like homework, going to be like the midterms. We're not going to do anything too surprising. I would say everything from the course is fair game. I'm probably, you need to know these things and able to do these things, although I probably won't ask you super detailed questions about the ARM instruction set, their workflow, tool chain, but memory map.io for certain, how do you talk to a timer or any of these other things without knowing what this is? So I wouldn't stress about these, but the core concepts here are required to know these things. So primarily we're going to look at interrupts, timers, serial communication, and analog and digital converters and digital converters. All right, so interrupts. So how do we get, anybody remember, how do we get information, like we have an ADC that's about to end, how does this thing tell the core that it has ended its ADC conversion?
The ready line goes up.
How does that happen? Ready line. Can you describe it?
It goes across the bus.
Across the bus. Anybody have a different interpretation? Yeah.
The the interrupt pin on the ADC gets tied to a GPIO, which internally is configured to go to the NVIC, and then when the NVIC detects that GPIO line is high, it sets the pending bit in the interrupt register, and something causes the ISR to run.
You guys both got a little bit. So the ADC gets data through the GPIO pins, but the ADC itself will have registers and the ability to throw an interrupt. The GPIO pins do it, of course, as well. But the key idea is it's an extra wire. It doesn't go through the bus. It's an extra signal, literally a wire, that goes to the NVIC. And we could draw them for every single device. Single peripheral could have them, and the buses have interrupts, and the DMA has an interrupt. And I'm sure if you have faults on your SRAM or something, there's interrupts. But there's lots of these wires, 96 wires for your particular devices you're using in lab, that will come back here, and each one of them can hold this interrupt state. So it doesn't go through the bus structure, because these peripherals can never talk directly to the core. Only the core, through the bus or high performance bus matrix, and through the bridge, can get to initiate conversation with these things. Say, okay, now it's your turn to talk. There's no way for a GPIO to say, hey, please talk to me. That has to be done with this external wire. And that is the same if you think about SBI or I2C or UART, well, not UART, SBI or I2C, these other communication protocols where they need a dedicated line to talk to, for the peripheral to talk to the core. Any questions about that? Yeah?
So that wire is only on the HB or peripherals? It doesn't apply to the APV ones?
That's for everything that has an interrupt. So I was saying like DMA has interrupts. That will be an extra wire that comes back through here. I bet the SRAM probably has a system fault interrupt or something where it says, oh, there's some error occurs, and that comes back. So we could draw up to 96 for interrupts for all these different wires for different conditions. All right. So here's a kind of more simplified example. Here we have some, what do my animations tell me? Okay, so here we have some interrupt that's going to occur. We've set up a GPIO pin. We've gone through the registers and said, on port A, pin 3, if there's a rising edge, I want you to throw an interrupt. Okay, so that will occur. The GPIO pin will throw a line that will go high to the NVIC, and this will be the IRQ. This is the interrupt request service line, and this tells the NVIC, hey, this thing has occurred, right? Now it's the NVIC's job to process it and decide which interrupt should be on first, second, third, if there's multiple. But this is just a request. Remember, there is going to be 96 requests coming in, so we're just showing one here. So the NVIC will figure what that is. Its job is to say, okay, IRQ is interrupt number 9. However, I need to go look into memory to figure out where this is. And where is the vector interrupt table stored?
Stored at the bottom.
Stored at, do you know the exact address where it starts?
0?
Nope. What's that?
Minus.
Nope, not minus. 4, yes. 4, we'll get to that later. we'll get to it next slide, but we'll see that 0 is the stack pointer, 4 is the beginning of the vector table. Okay. Anyway, so now the NVIC has to figure out, okay, which is the actual handler. So it goes into the interrupt table, figures out what address that is, and then sends that to the core to actually execute the interrupt. We can see that through here a little bit. Oops. So here, this just shows the top of the stack, and this is the first reset handler. This is the most important one. This is when you power on, nothing can interrupt this one. And then all these other ones. These first 16 or first slots here are all the ones that ARM instantiates as part of their architecture that must be there. So sysstick timer, these debug timers and hard fault timers and bus faults, those have to be there. And then these 16 and up are all the device manufacturers, so ARM and AMD and STM, NXP, those sorts of manufacturers will have interrupts that they are customizing based on their hardware. So it's not required to have a watchdog timer as part of ARM's architecture, but STM has added one and says, okay, this is the location. So hex 40 holds the address for where the interrupt handler is for watchdog timer. And so these interrupts come in, the NVIC figures out what address should be done. So for IRQ 3 over there, is stored in hex 64, that's the address in the table, and then that points to some IRQ handler, some memory location. And so we have our interrupts. So here you're in user land, so this is time. We're going to show different on top is going to be the hardware actions. So an interrupt occurs, we're going to do stacking. What is stacking? This is how the NVIC gets the processor from normal process mode into interrupt mode. And so what it does, it has to retain the entire state of the ARM, of the core, such that when it returns, it can go back into position. So we already learned about how you need to have ABI compliance, so you need to keep these bottom 4, but you also need R4, the link register, program counter, and then the program status register, so that you know where the URL flags or the ALU flags are and those other flags. So when you go back to your program, you're exactly in the right position. So here you go execute your interrupt handler, you'll be done, and then it'll unstack, taking all of that back, put it back on the core, and this process of stacking unstack makes the entire interrupt transparent to the core. The core doesn't really know that it happened, all the state was retained. It's just that there's a missing gap of time. Questions are there? Remember this? Must be one question. There must be somebody, some brave person here has a question. Fantastic.
Is that when the LR is set to be like near the top of the memory?
Yep. Hardware does it. So there's a hardware function that basically goes, and you don't, as a programmer, don't do anything, but hardware will cause all these things to be pushed onto the stack.
But unstacking isn't hardware, or it's just...
Unstacking is hardware as well. It's when you, in that particular case, so here, I'm not showing it here, but the return, oh yeah, here it is. So the link register, when you stack, or when you're in your interrupt handler, this is your link register. And so when you exit your interrupt, you go here. What is this? This is a signal to your hardware. If you try to execute this code, your hardware says, oh, I know what I'm supposed to do. I'm supposed to unstack.
Oh, wait, so... Oh, I thought that, like, there was code at FFFF9 that did the unstacking. That's not what happens?
We could say it's hardware code. You could say it's code that you don't write. It's
stacking hardware code?
Yeah, you can say that. Okay. How do they actually do it? I don't know. But I'm going to guess that ARM probably has RTL. Right. So what does RTL stand for? Does anybody remember? Register, yeah. Transfer language, right? So they've probably written RTL, which is, I guess is a version of code that's burned into hardware that does this task every single time. There's probably not code that can be modified that's doing the task. Yeah. So what do we do? We're here. Any other questions? Yeah.
So hardware will store all these
Correct. All those, yes. Yep. So it doesn't do, so the question was, so hardware will do all this? Yes, hardware does all this, puts it on the stack. It doesn't do like R7 through R11, because there is some ABI compliance, so it wants to make sure. It says you probably don't need those if you're in a interrupt. So when you write your interrupt handler, you can't go and use R11 through R4 unless you store those to the stack, do your task, and bring them back down before you leave. So your handler still has to be ABI compliant. And again, this is done in hardware. And so it's probably valuable to kind of think through how your code, your core, and your stack are all interacting together. So in this particular case, stacking occurred, which took all these values, put them on the stack, allow the handler to come in, change the stack or the PC to something else, able to run all of this stuff in sysdict handler, and then on the way back, it goes and executes this thing, which causes all of that to be restacked on top there, and normal code keeps executing. The only caveat is the core will complete whatever instructions it's doing. If it's a multi-cycle instruction, it will not split halfway in the middle of an instruction. It's not a valid thing for this architecture. All right, so steps for interrupt. We'll go through these. So you have some peripheral, some other source, raises interrupt, and determines which one it should be. Hardware stacks. There's some idle time while you get the bus and you fetch things. So the target, there's like 6 cycles, I think, or maybe 12 cycles, I forget how many it takes to get into an interrupt. It updates the stack pointer, updates these program status registers. This is the lower part of the PSR. With the exception numbers, sets the PC to the vector handler, and then updates the LR. So those are the steps to get. Oh, and then I missed it here. The latency is 12 cycles to get in. Can't remember all my processors. It's also good to think through these diagrams. So what happens when we have multiple and concurrent overlapping interrupts? What happens when your interrupts get interrupted? And so in this particular case, we're showing program stack, and then some interrupt occurs. Well, what happens if you get an interrupt here? Thinking through which one has a higher priority, which one has a lower priority, difference between preemption priority and sub-priority. And then we have the different conditions here of preemption, tail chaining, and late arrivals. Preemption just states that if an interrupt happens when there's an interrupt, and it's a more important one or has a lower priority number, then it will interrupt the interrupt. Alternatively, if it's not a higher priority, then it's likely to do tail chaining, such that instead of unstacking, it will go and spend just 6 cycles and then go to the next interrupt without having to do the process of unstacking. Then late arrival says, basically, if you start an interrupt, but before you start executing it, another interrupt comes, so an interrupt comes here. You don't go into this one. You can check in this last cycle here of the stacking process and then just switch the program, the PC counter, because that's the same thing. The PC will go in, you switch that PC, and you'll actually do the late arriving ISR if it is higher priority or more important than the pending one that caused this original interrupt. Super clear? Why don't you guys talk to each other for about a minute and ask each other if they have any questions. What would you most want to know about interrupts? what are you most confused about interrupts? Maybe that will generate some questions. Why don't you guys talk with each other? You can even use this slide or these concepts as a prompt. Go ahead.
Good sense to me. Remember later rivals to figure out.
Tony Valencia.
Usually it's like it's sending like interrupts.
I didn't know about it an hour ago. Makes sense. About interrupt priorities, I assume it's like
Extra 8 last nature back the other day. Another one's I have.
that's the part that
How much space did you respond? You went 10?
looks at preemption.
Interrupt again during stacking.
Answering stuff like 30.
I know.
I think has a higher priority.
All right, what questions do you have, or what question did your neighbor have?
Interrupting interrupts. It looks at preemption priority, then sub priority, then interrupt number.
It looks at preemption priority, because sub priority, so preemption priority allows you to preempt an interrupt, but sub priority says of things that are pending, what is the order? So a sub priority number would not be the deciding factor if an interrupt should be interrupted.
Okay, so, but if two interrupts have the same preemption priority but different sub priorities, then it wouldn't be interrupted.
Right. So two interrupts come in, so same interrupt priority, they both go on pending, right? And then which one goes first? Well, then you look at the sub priority number to determine which one goes first.
But if there's already one going,
Then you would wait.
it wouldn't-
Yeah, so if two interrupts come here, both with less important interrupts with higher interrupt numbers, but less important this one, they're gonna wait till the end. And then the sub priority number is gonna decide of the things that are pending, which one will go next.
If you have two interrupts with the same preemption priority but different sub priorities, and they arrive at the same time, which one's picked? Does the sub priority matter in that scenario? It's not like you're going off an interrupt. Those are just the first two interrupts.
So, okay, so you're here, two interrupts come in, and one has a more important
Sub priority,
sub priority.
but they have the same preemption.
Then they're both gonna be, I think it's whichever one has a lower sub priority, because then they are still in this case, it's the same case here, you have two things that are pending, right? And then how do you sort the pending interrupts? Well, you sort the pending interrupts by sub priority. Preemption priority, then sub priority.
Because okay, so like for in the case where you're in and out already, it makes sense to have a lot of things pending because like you're in this interrupt but nothing's preempting it because nothing can preempt it, so a lot of things can like build up in that interval. But if you're just in the program, you interrupt on the first interrupt ever possible. So like
Correct.
that was the confusion I had.
But I'm here, so say the interrupt happened and then what happens just a cycle later or less, right? Then you're still in that stacking. You might be in a late arrival case because you're gonna look in which one, do they have the same priority? Okay, fine. Then it's gonna look for sub priority and figure out, because you haven't entered an interrupt yet. You still have time to choose your interrupt. Does that make sense?
Oh, okay, so that's during stacking. Also, like if another interrupt happens during the stack, it would have some special hardware to change the address of the PC.
Essentially, the decision of which interrupt to go in does not need to happen while you're stacking. You don't need to know here which interrupt should occur because you're going to have 12 cycles to here. So you just need to know right here which, you go from the NVIC, says this chooses the one, whichever criteria, and then in that last cycle says this is the PC. Go to this PC.
Okay. So it could drive on cycles 1 through 11, but then cycle 12 you would need to that would be the
Correct.
okay.
Yeah.
Can you explain what's happening in tail chaining and late arrival?
So tail chaining, here I can go find some actual slides that teach things. All right, what do we have here? We have tail chaining. So we are in an interrupt, we've stacked. We are in interrupt IR4, which has set the base priority here. Only one thing is pending. Oh, because I'm not sure why one thing is pending. Enabled. It should be active. Let's see what happens next. So now we get another interrupt. Oh, I think I just had my slide sequence out of order. It causes IRQ1 to go into pending. And so you don't want to do preemption, or you don't preempt because it has a, let's see, 1 has a higher priority number, but is less important than 6. So the base priority says you can't interrupt me. And what you don't, and then when you exit the IRQ that's running, you, instead of going and unstacking, which would be inefficient, you use tail chaining, which is less time. It only takes 6 cycles here. And then it just goes to the next interrupt, the one that was pending. So basically, to get back to your main program, everything on pending would have to be empty. You'd have to have all zeros here. And nothing would have to be active. And then you can go back. And basically, at any one point, if there's anything pending, the NVIC is deciding, well, what's pending, first of all, and then if there are multiple things pending, what's the order supposed to be? That answer, I forget who asked the question. Did that answer the question? No.
Yeah, I guess like maybe I'm just missing like what is it that's actually causing the fewer cycles? Like so you're not unstacking.
Well, the architects have made a choice to help improve performance. So rather than unstacking and restacking, it's just taking 6 cycles, don't know what it's doing, to get basically the next PC and put it in there.
So that's just something that they've optimized. We don't really know the details of how that's
You just have to know that the optimization occurred for your benefit. Yeah.
So as long as you have everything pending and you have nothing preempting, like another interrupt, you're tail chaining.
Yeah, so, well, you'd have to have something pending to here, something would be pending. IRQ1 comes in, now at this point in time we have something pending. You have something active, and then because the base priority, here. Base priority is 6, but this interrupt priority is 10. This won't get done, so that demands that it stays pending until this this gets done, and then it will go to tail chaining. It basically is the method of clearing the queue without having to waste time unstacking.
Also, one thing I was wondering, if you have the same preemptive and sub-priority, is it steady priority, like,
Is it, if you have the same preemption and then different sub-priorities?
Same sub-priority.
Same sub-priorities, my guess is gonna go by the NVIC table to break the tie, right? Because now you basically have a tie. How are you gonna solve that problem? Well, the NVIC table has an ordering of what's important and what's not important. So I'm going to guess that does the lowest value on the NVIC table. Any other, you wanna go through, you asked 2 questions. You wanna also go through late arrivals?
Yeah, I think that'd be great.
Sure. Late arrivals is you're in a program and some interrupt has occurred. Interrupt 4 occurs here, and it goes into stacking. But while you're doing that, interrupt 3 occurs. Well, interrupt 3 has a lower priority number, meaning that it's more important than 6. So instead of going here and then like stacking again or something, you wouldn't want to stack and stack again. It would just be wasteful, right? It's possible. I mean, you could technically do it. It would work. But the double stacking is wasteful. So instead, what we do is this: at the last moment, you come in here and you go to IRQ3. So basically, we look here. There's multiple things pending. Should I get this right? Maybe I got it. Oh yeah, there's multiple things pending, and not until that shouldn't be there, but not until you get here do you go and sort through and figure out which one you should actually use, and then you use the one that has the highest or the best priority and the best sub-priority. Okay. Any other interrupt-related questions?
Late arrivals for unstacking too.
For unstacking, what does that mean?
So while you're unstacking from RQ4 right there, so RQ5 happens while you're unstacking, would it like?
That's a good question. You don't want to interrupt unstacking. You don't want half your stuff stacked over here, right? And you don't want to be, you can't like stop stacking halfway. And if you get here, well then you're back to your main program. So then you would have to stack again.
What about late arrivals on the tail training?
Late arrivals on tail chaining. You're writing the exam questions for me. Late arrivals on tail chaining. So you're saying here.
Yeah.
I assume that in the last cycle, if the interrupt occurred here, it won't mess up the program, so then you can still go through here and then choose to that next interrupt.
So generally, nothing should interrupt the stacking or unstacking process.
Correct. This has to be atomic. Any other interrupt-related questions? All right. Let's talk about timers. So it's important to remember the base structure of a timer. You have some clock coming in. This clock comes from an external crystal, maybe an on-device ring oscillator. It may be a crystal attached to a PLL, but some known consistent time source comes externally to this peripheral. You have the choice to use a prescaler, or you could use a clock divider, but this gives you the flexibility to slow it down. Why would you ever want to slow down the clock to a timer? It seems like it would just be worse. Like you just make things slow and now you can't do things as fast. Why are they giving you this choice?
Depending on your application, you might need different like periods or different pulse waves to do whatever you want to do. And prescaling gives you that flexibility.
Yeah, I think that's exactly right. I would say maybe a more precise way to say that is there are applications that you want to measure longer periods of time and you're willing to give up the time resolution. That's exactly right. And now this counter module is simply just a counter that's counting up or counting down, and every time it gets an edge in, it increments its counter. So just 1, 2, 3, 4, and sometimes we would show that as a ladder going up. And because it would be too hard to show the stair steps, sometimes we just show a straight line that as time goes forward, the count starts rising up. The output of the timer is just going to be a digital value, some number. And you can have an ISR module that will say, well, when you hit, or when this thing hits a certain condition, say like it's 0 or FFF, whatever the top is, then it will throw off an ISR. Also, when the event occurs, you can have an auto reload register. This auto reload register will restart this timer at a certain value. An easy one is 0. So you're just going to count up to some threshold, and then you're going to wrap back down. Another one is if you're counting down, this will be the top, and you'll say, I want hex, AAAA, and then it'll count down from that. And when it reaches that overflow or underflow value, an ISR will go off, or can go off if you've configured it that way. And then we add this extra module. To get more functionality out of this, we add this extra module. We call it a capture compare module because it has different capabilities. So the capture capability says, when some event occurs, I'm going to capture whatever digital value stored on here. I'm just going to hold it in the register so that the core can look at it later. And so typically, maybe that would be a GPIO pin that will go high. Maybe you'd have a GPIO pin that will cause the timer, GPIO pin that will go off, and you'll count the time. You'll say, it's 001, and then you'll have another interrupt that goes past another period of time, and you can read that out and put it in your core. And then the interrupt will come again. Maybe it's that magnet on the fan from the problem, a homework problem. And then you can go read through this thing again and say, what's the delta between this time, that new time I got when the second pulse came in versus the previous time, and you can calculate the time interval between events. So typically, the capture timer, which is maybe an under-celebrated thing compared to the PWM generation, is a way to capture or measure external event, the passage of external time, or passage of time based on external events. And then that has its own ISR block so that you can know, okay, some timer event occurred, and then your interrupt handler, you can go and grab the value out of this and store it for later use. What questions do we have here? Yeah.
I might be jumping ahead, but can you talk about this diagram in like relation to the RCR?
RCR. What's the RCR?
Or the repetition counter register? I know it's not on this diagram.
Oh, repetition counter register just says, especially for the compare mode, says how many times you want this to keep going. So when you're making a pulse width modulation, that's a classic example, you can say, I want this to go for 10 pulses, rather than say I want it to go continuously or just for one pulse.
Okay. The reason I asked that is I saw a question on the practice, one of the practice exams. So that doesn't affect the period at all, right?
I don't see how it would. Why?
No, I was just confused, but.
Yeah, it shouldn't affect the period, but it affects how many periods occurred.
Okay, that's what it is. Thank you.
Yep. Yeah. So that's just the same thing I just said. The counter example is the compare. So the compare says when this thing hits a certain value, then do a task, right? So you can go and set this counter to count from 0 up to FFF, and when it hits, I don't know, 11111, then an interrupt goes off, and then some task can occur, right? And so that's the basis for pulse width modulation, and that's where we get. Here we have examples of counters going up, counters coming down. You can do the seesaw up and down, so this gives you twice as long while keeping that same resolution. And then we go and turn this thing on with the capture compare registers. We can turn these ramping functions. So this is time, this is the count of the counter. We can say, here's our capture compare register, and now we're going to do a task. What's that task? We're going to turn a GPIO pin high or low at this point, and then when you overflow, it goes back down, and now you're essentially making this pulse width modulation to control an LED or a motor or something. So why need to, oh, 2 questions, yeah.
So if you were trying to have some interrupt occur like at a known frequency,
yep.
Would you use the ARR like underflow overflow, or would you use the like CCR?
You could use either. CCR gives you some flexibility. AR will work. The challenge is that it only allows you to have one interrupt, while you could have multiple CCRs that would have interrupts at different times. So either one is fine. Is kind of let's see, I think on your particular microcontroller you have like 6 or 7 maybe timers. Maybe it's more, I forget. But if you were running out of timers, you might use your CCR, but have like 4 channels on that, and then you could have multiple ISRs going off. There's another one, yeah.
What's the difference between the capture and compare?
The capture and compare is what triggers it. That's kind of a big conceptual difference. So a capture is external world. So this causes this thing to capture the value that's stored in the timer, okay? And then it reports that to the core, typically through an ISR. So it just says, since I was told to start, this is how much time has gone past, okay? The compare, I guess I didn't go through this. The compare is looking at some value. So you have some counter here, you have some compare value here, and what happens is you're just trying to see, does this number equal this number? If it does, then throw it off an ISR. Yeah.
So now you think about it as capture like a stopwatch and compares it like an alarm or something.
Yeah, that's a good analogy. Yeah.
Can you go back to your pulse width modulation mode slide?
Sure.
Yeah. So here, like, let's say, like the reference is just like 5 or whatever. So for the CCR, if you're above 5, then you have your PWM on.
Yep.
And so when you reset, let's say that's at like 6 or something, right?
Yep.
Is your, this is where I get confused. Is your ARR 0 because you reset back to 0, or is it 6?
In this particular case, your AAR is this value. Okay. It says you're going to count up to your AAR, and then you're going to reset down to 0.
Okay, and then let's say like, what is the value of zero call? Like, let's say I want to like reset down to like 3 instead.
Well, okay, so the AAR either sets what, when the counter reset, what it counts up to if you're in count up mode. If you're in count down mode, it tells you what the counter starts at. So AAR is always kind of this peak regardless of how you've set up your structure. So this is the AAR here, and this is the AAR here. It's just kind of like from the perspective of, here I'm going to count from my AAR down to 0, then do a task. Here I'm going to start at 0 and count up to the AAR. Either way, this AAR is setting the period.
As far as the mode, when it comes to up counting and down counting, would that be more of like something given like mode 1 for like being high when you're less?
I would tell you. I don't want to remember that. I don't want you to remember that. That's not important to remember. Like, you have to remember how timers work and like how PWMs work, but like labels like this mode 1 versus mode 2 is probably not something I'm excited to test on. All right, why don't you take a minute, talk to each other, figure out what questions you have about timers.
So it's like
That's my question. Yeah. I'm gonna hit the bathroom real quick before you start the next time.
Depend on the example, actually.
What are you most confused about?
Honestly, you just. Why would you ever use
That's what you should be asking. What is that thing I'm most terrified of? Any timer question whatsoever.
By setting the number that you either like 1 hertz PWM 50% cycle.
Yeah.
We're able to choose.
Oh yeah, you check
I can all see why you should use anything other than dunk counting.
is like calculating minus my other PWM.
If you
Think of anything you shouldn't use.
I think on the advanced timers, you can set up different interrupts based on different channels. So a lot of them have, it's not just one CCR, it's multiple. Here, I'll just tell everybody this.
Capture just grabs what you
Nah, it doesn't matter. It has multiple CCRs, and now you can use these ones to set off different interrupts. So it's a way to control which interrupts go off on a time basis. So that way you're not externally setting anything.
And then you would just like
No, so you want, well, say you want every, 13 seconds, you want an interrupt to go off so that you do some task. What's that task? I don't know. Maybe you want to sample an ADC. Maybe you want to measure something. And so you could use a timer to do that.
Maybe this way you can have it.
Yeah, you could do that. And so you could use different CCRs for that. All right, what questions do you have? What are you most terrified to get on this exam? That's the question you should probably be asking now, so we get it answered for you.
To clarify,
Hold on. Yeah.
so when you have capture, it's caused by the GPIO output, grabs the timer value, puts that
Yeah.
RQ, but then there, it's caused by the timer, but it's still grabbing the timer value and putting that in the IRQ.
It's comparing, it's comparing what you set that CCR register for. So I want you to go off at this time, 10 o'clock. So it's constantly every minute or every microsecond, whatever, looking at the clock and says, is it 10 o'clock? Is it 10 o'clock? Is it 10 o'clock? Finally, it's 10 o'clock. Then it throws off an alarm.
Okay, so it's just like a pause, like it is on.
Yep. Yep. And it doesn't always have to be a GPO. I'm sure there's other things you use for compare. That's just a pretty easy one to think about.
this capture uses.
Are PWM modes related to the compare output? Yeah. So some of the different modes are dependent on how you've constructed your timer schema and the polarity of your logic here. So if you're like counting down, but this is inverted, that's one mode. If you're counting up and it's inverted, that's a different mode. So it's kind of like, what are all the logical combinations here? So this is counting up, counting down, and then this is inverted logic or non-inverted logic. So that gives you all the different modes. I'll just tell you on an exam what I'm looking for. I'm not going to ask you to remember which mode corresponds to which logic level here. Yeah.
Earlier you mentioned that the center counting mode, so you can get like a larger width with like resolution. Is there a particular example where one would use that option compared to just using up counting or down counting?
I'm sorry, I missed the first part.
And that's the center counting.
Oh, center counting.
You've got like that larger, longer pulse with the same resolution.
Well, so here the problem is, if I double the period, I have my resolution, right? Because now I have to spend twice as long for each step. Here, I don't have that problem. Here I go count up to my AAR and back down, so I can double my period while keeping the same resolution. It seems like an edge condition. Like, how often is an engineer in the world faced with that condition? Like, oh my gosh, this is the solution. But my guess is it's so easy to implement from a hardware point of view. They're like, we'll just give it out to the engineers and see if they use it. And we can construct, there's lots of complicated ways to construct pulse width modulation, especially if you have multiple things that I'm going to guess there's maybe other cases where it's useful, but really all it's giving you is double the period with the same resolution. That's the trade-off. No other questions about timers? Yeah.
Can you kind of explain like how like intuitively you get like the math equations based off of like the ARR values or like the CCR? Like how do you like read those out?
So I think the core is to always think about this as timers are counting clock periods, right? So your period is your AAR. So that's just saying I'm going to count up my AAR value times the period that's going in after my prescaler. So this is a period, and this thing counts periods up until that point, or starting at that point. So that sets my period of my, or sorry, this thing counts time periods here up until the period of my pulse width modulation. And then the CCR, let me find a slightly better graphic for this. Maybe this is a good graphic. Right, so here I have a clock coming in and I'm counting up to an AAR. The AAR is 6, so I'm just counting clock periods. I could change my prescaler to make those periods longer, and then I'm counting more periods of time. But basically the AR is just counting up to here. And then their CCR is just saying, hey, when do I make the decision between when this thing should go high or low? And so that's basically, the period divided by your CCR is going to give you your CCR divided by your period is going to go and give you your pulse width modulation, assuming that it's a positive pulse. I don't know, that's how I usually think about it. Does that answer your question? Yeah. Any last, yep.
So I thought, so the RCR here is 0, right? I thought that meant how many periods happen. So are you saying that within 0 to 6 counting thing, there's 0?
Our RCR here is, now we're all perfect. We're all said, okay, if you go for 1, I'm going to get 1 pulse. I'm going to 2 for 2 pulses, 3 for 3 pulses, except for 0. 0 means going continuously forever.
So if you don't want to mess with it, you just put the 0?
Yeah, and it keeps on going. That's the default state when you power on, so it won't, I don't think you even have to set it. All right. Any other timer-related questions? Yep.
Your CCs, the relationship between your CCR and the ARR, and sort of like defining the duty cycle, like how much.
Yeah. Yep. And remember, we do horrible things to you because those ARM engineers, architects are trying to trick you. They have things like your program, your prescaler has to be that value +1. Oh, those mean engineers. Why are they adding that +1? to a prescaler?
Don't trust you.
Why do you mean they don't trust you? Right, because you can't take your clock value and divide it by 0. That makes the whole thing stop. It's always at least got to be divided by 1, and then it could be 1 plus some value. So they're always giving you this offset 1. Same with, I think your CCR is also the same way. I have to go look it up. But just remember those tricks as you go through the homework and practice exams. Sometimes there's this +1, and you just have to think about in the math why that exists. Yep. Oh, is it the AR? Yeah, auto reload register cannot be 0. Oh, that's true. If your auto reload register is 0, then you go from 0 to 0 in 1 clock cycle, and it's bad news bears, right? Your timer is constantly going off. So it's the AR, not your CCR. Okay. Let's do a quick review of serial communications. So most of serial communication is talking about one chip talking to another chip. You can think about chip or devices talking to each other also as the peripheral is talking to the ABA, the Advanced Peripheral Bus Bridge. That's a different type of device talking to each other. It obeys a lot of the same structural issues. It's just a parallel bus instead of a serial bus. Why is it that we don't have a lot of parallel buses when we're talking from chip to chip? What's the design constraint that we typically don't have it?
You want to use the least amount of GPIO pins possible.
So pins is the problem. And you don't think about this as being a realistic problem, but remember if your piece of silicon is only like 1 millimeter by 1 millimeter, there's only so many pins you can put on there to actually get data out to the external world. So especially little microcontrollers are really pin constrained, while bigger chips like processors, they're also pin constrained, but they're also larger and can do more tasks. So I/O bandwidth getting off device is usually much more restrictive than going from one module to another module on your device. So it's just good to keep that constraint in the back of your mind. That helps you understand why these designers are making these weird choices that impact us. So UART is this kind of ancient communication protocol going back to the early 80s. And it was for computer to computer, but as computers got more complicated, now this protocol still exists and is good for chip to chip. And so we have one device that talks to another device. The wiring trick here is that RX goes to, or TX goes to RX, and TX goes to RX. TX does not go to TX. Don't do the problem that I did when I made my first board and go TX to TX. That was bad news bears. Then I had to go take my little X-Acto knife and cut those wires and then solder Brit or put little blue wires on my board to make it work the first time. But regardless of that, TX goes to RX, TX goes to RX here. And now you have these two devices that talk to each other, but they have no clock. And that was the real trick of this protocol. How do you get around this clock issue? Well, what you do is you have to a priori talk to each other or know what approximately the clock speed is. So we call that the baud rate. And this protocol is approximately a 10% error. That's true, although that would still cause a lot of, with noise and everything, would cause a lot of problems. Usually you want your error to be much smaller than that. But what happens is, do we have a, no, we don't have it. What happens here is that you're going to run a timer that oversamples. Is probably 8 to maybe 16 times faster. You find the starting edge here, you start your timer, you count over half a bit here, then a full bit here, and then you know that you should be counting in this thing. So it's really the starting condition where the sender, whichever one, it doesn't matter, it's a fully symmetrical protocol, whichever one pulls the line low first, starts talking, and then the other one knows it needs to sample here, here, here. And we know what the protocol size is. It can be lowest bit, least significant bit, most significant bit, but then it has predefined sizes, 5, 6, 7, or 8 bits. You have a parity bit and maybe 1 or 2 stop bits. Any questions about UART? Yeah.
So is this the baud rate is defining how fast data is going to be sent so that each one can set the clock to the correct oversampling?
Correct.
Right? Okay.
Yep, exactly. So you have, like other devices like SPI and UART, they have a clock. So you don't have to agree beforehand what the clock rate is going to be. But this one you do have to agree beforehand what the clock rate will be. The trick is you just don't know when the clock edges are coming. So you need this oversampling to figure out the correct phase of the signal. And there's just an example. One of the tricks is UART is both devices can talk simultaneously. They both have their individual lines. So it's not a requirement that one talks before the other one and back and forth, although that's typically how it was. Usually, say the one device is asking a question or telling it a command, the other one responds. But it's totally legitimate for both to be talking exactly at the same time on different wires. Both would be trying to do clock recovery and figure out when to sample the data, and then their registers would get full, and then the interrupt would go off, and then each microcontroller device would have to go and service that interrupt and figure out what message was just sent. Talk about SPI. This one's probably the closest to the advanced peripheral bus that we studied in the first part of the semester. So here we have a minimum of 4 wires. We have serial data out, serial data in. So that is shared pins that go to every device. So the controller here has serial data out. It's from its perspective. Has a bus that goes to everything. It has a serial data out here that goes to serial data in that goes to every bus. And there's also a clock that's shared with everything. To do arbitration, to control and understand which peripheral should be talking, the chip select line comes in, and the chip select line is lowered to select a specific chip. So whichever one of these it wants to talk to, it will pull that thing low. And then, only then, the peripheral knows that it's time for it to communicate. It will listen and send data back or respond when asked. Checks are slow, generates the clock. The clock is not always going. The clock is only going when the controller sends it out, only when it wants to communicate. And then technically it's shifting data into one and out the other one at the same time, although in practice, that's not how it would appear on the oscilloscope. In practice, the controller will ask or send a command, and then the peripheral will respond if it needs to. Any questions? Yeah.
For the serial data in the SPI controller, that's connected to the 3 peripherals.
Correct.
So is it like detached from the wire depending on the muxes depend on the chip select?
The mux, what are we talking about? Chips?
Okay, so all the SDIs on the peripheral 1 through 3.
Yep. Only
not interfere with each other.
A peripheral can only talk when it's been selected, right? So the controller is responsible for only selecting one of the peripherals at a time. Therefore, there's only 1 bit of data going out on that bus. What do you think about that? Did I answer a different question? You give me a look like I don't think you did the right thing.
But I get that peripheral is selected. Like, how does that work? I guess
this chip select line has gone low. This thing chose to talk to this one. This is the only one that should be sending data out on that net.
I guess like how do you send out the data without it like interfering with the other SDOs?
Oh, like this SDO is pulling low, and this SDO is pulling low, but this one's been selected, like this has a CMOS output.
Yeah.
This one is going to go into high impedance so that this one can go high or low. It just tells, the chip select tells which one should attach to the bus. But internally, it takes care of that.
Okay. So it's like this open tree?
No.
All of the serial protocols use
Shift registers? Like, why is this a bullet point on SPI specifically?
All this shit, yes, all the protocols use shift registers. SPI was originally set up such that one shift register from the controller would be shifting in data from the other one. That's how it was originally set up. It's just that typically what happens is this one's going to send out like all zeros because it has no data to report.
Oh, okay.
So you can only talk to one peripheral at a time?
The way it's wired, it's sort of like
That is the typical usage case. There's nothing also because SPI is not does not have a specification like I2C is. It's more an emergent protocol. You could definitely have a controller if the peripherals behaved properly, could broadcast to all of them and say pull all their chips low and say here's the command. Now they can't all talk back at the same time. So it's possible. I don't know of any chips I can remember that actually do it though. All right, then we had this awesome confusing diagram. Do you know how good this diagram is? Once you understand this diagram, oh, your life is going to be so happy. It's going to be great. What this diagram is trying to explain to you is that you can have 4 different operating modes for SPI, and it's all about, well, the clock polarity. Is the clock normally start high or does the clock normally start low? Okay? And then it has, well, when is the data sampled? Is this data sampled on, in this case, the first edge transition or the second edge transition? So now that gives you, 2 by 2 gives you 4 different operating modes, and then this diagram is just trying to show you, given a stable set of bits to clock in, they've offset the clocks. Here they're showing the clock polarity high, and what are we in this mode over here? So we're in one mode, so we're in mode 3. On the second transition, we're clocking data in, and it's just showing you where you're clocking, and then you can work your way through this diagram to understand all the different modes at which your clock and your phase, clock polarity and your clocking edge will be used to clock in data.
Does the diagram basically show that no matter what mode you're in, you're going to clock the data at the same time?
Yeah, the real purpose of the diagram is to show you where on this clocking edge you will be clocking. But yes, I guess the other thing it shows is that no matter what clocking mode you are, you can clock in the middle of the data. Yeah.
What's the benefit of having 4 different options for clocking?
I don't know. And we inherited this stuff. I'm just reporting. I'm like a news reporter. I'm telling you this is what industry is doing. You're making your life worse. I don't know. It has given flexibility to industry to create different protocols in different ways. Maybe they had chips that could perform better, I don't know, in one clocking scheme or another one. It used to be that you would worry about this way more while your peripheral that you buy may be in mode 3, but your microcontroller can only do mode 1, and then you were screwed. But now it's everything, the logic is cheap enough that everybody can adapt more or less. It may be the case that you'd have a peripheral, different peripherals will have different modes. And so if you go back up to here, right, this could be mode 3 and this could be mode 1. Right, that would be horrible. It's fine. The microcontroller just have to know that and knows when you chip select something, now I change my mode so that I can talk to that. That's more common. And this is just showing what a typical transaction is. We're only going to put out clock edges when we're actually communicating. So here, the clock has gone out, SDO has sent data out, and then it's the microcontroller that sends out the clock cycles, and this thing knows to respond back. It knows why, because it got this command here, and it responds in this particular case with F. I don't know why, it just does. But it's the microcontroller or the controller that's sending out the clock edges, which this thing is clocking data into. Yeah.
On the homework, I got confused by the fact that like you can have different numbers of bits you're sending, but like since it doesn't tell you how many bits you're sending, like from a stability perspective, is it okay to have like the last bit be sent when it's on its last clock edge, or would it need to be a bit sent before that? So like, you see how 7 on the top, or like up there, and then if you go down to 0, could you then have a 1 after that, or would that seem like not allowed?
Well, then you'd want, well, first of all, chip select should only go up after you're done with the things. Chip select's indicating that you're still in a transaction. So in that case, chip select would have to go out if there's a 1 here, right? And then you'd still need another clock edge to clock that thing in.
Okay. So if by the time we see that last go up and stay,
yep.
we know that in this case, we'd only be able to have 8 bits, not
Yeah.
9 bits.
But it's not that the microcontroller has to figure it out or anything. It's that you should have read the data sheet and already know what the protocol is supposed to be. So there should never be a case where the microcontroller is like, oh, I had to kind of figure it out. It should just know.
On the exam, would we know how many bits of data it's sending?
Yeah, I'd have to tell you that. Or you could make it up. You could say, I assume it's 0 bits. Although that would be a hard time to give you points. You could say, I assume it's 8 bits, because it's standard.
And you were saying earlier that the standard we're going to work with is we're sending and then we're responding.
That's typically
at the same time, since they can't happen at the same time.
It can happen at the same time. It's just that's not how people use the protocol anymore.
In the case where you would need.
Maybe you want to have high bandwidth data transfer. There's like these cameras that stream data back, and then you can also set up it's like quad SPI, so you actually have 4 data lines on SPI, and you can send data to configure the camera for the next thing while data is coming back. So there's cases where it's possible. It's just not what we're trying to focus on in this class.
This is a curiosity question, but like, let's say you're sending out that S, right? Would you be able to send it to multiple peripherals at the same time? Or would that get in the way since you need your chip select line?
So I think it depends on let's assume the peripherals are game. Let's assume all the peripherals have the same mode. That would be the first important one. If there are different modes, that wouldn't work. And then the controller could pull down multiple lines to send out a thing to each. Basically, for that to happen, each peripheral would have to basically have a broadcast mode or condition, right? Where like they expect that to actually happen. Because what you wouldn't want to have happen is then, how do you control which one do you talk to next? Like this thing would have to do it. Yeah, it seems messy. Yep.
Peripheral respond with a variable number of bits, or it's fixed?
It should be fixed.
Okay. And is there like some? I guess what I'm trying to understand is like, is there then like a counter that knows how many bits it's like waiting to receive, so that it knows to set the chip select high when it receives that number of bits?
Essentially, yes. Yeah. So inside your device, you're going to set up, and your peripheral, you say there's a register, like a shift register, that's collecting these bits, and you're going to say, this is how I've set up my device, this is how many bits I expect.
Okay. But each of the peripherals can have different numbers of bits, or?
Sure.
Okay.
They typically don't, but they could.
Okay.
Yep.
We usually send like the most significant bits first, or like the least.
There's no spec for this protocol, so you have to look in the data sheet and find out. All right. So we'll go on to I squared C. So this one, so let's see. If you think about UR as being the original, it was good for one device talking to another device. SPI, we could say, well, SPI solved that problem by being able to talk to N devices, but with the penalty that you have to have a chip select line for each one. It made arbitration, the task of choosing which one to talk to, very explicit, but it doesn't scale particularly well if you have lots of devices. So I2C attempts to solve this problem. I2C is attempting to reduce the number of wires to as small number as possible. So here we only need 2 wires, serial data and serial clock. But the arbitration task now is done by a address that's burned at manufacture time into each individual one. I shouldn't even say that. It's at the RTL level, hardware level, it's fixed. It's not dynamically assigned at manufacturing, it's fixed. Each device has its own address. And now a controller to talk to it has to know what addresses are on the thing. That's fine, you're a designer. You already know what the board layout is. Then the controller says, I want to talk to this device or that specific device. And then it can send data in. It says, I want to talk to this device and send data, or I want to talk to this device and receive data. And the other wild thing about this one is that you have to have these horrible resistors. These horrible resistors have the benefit of allowing one data line for controller to talk to a peripheral and a peripheral talking to the controller, because these are both open drains here. And now there's no condition where the peripheral, so you had multiple peripherals, or even just the one peripheral, can be driving a 1, and this other peripheral could be driving a 0, causing a short here. They can't do that. Only this thing can pull up current. So this one can either do high impedance, as in this thing pulls up to high, or they can both pull down to low, which will cause current to pull this low, but it won't blow anything up. So to share this one data lines that either one can talk on, they have to have this open drain architecture. The same, yeah. What questions do we have?
I have more question about like converting this from like pull up to pull down. I think it's about like using like transistors and I could like keep this like a default low. Like, I guess what does that look like?
So you can just go, so these are NMOS transistors, you could put PMOS transistors in here. And then you could take your resistor and put that to ground. So it would work, it's just that now everything has to be at the same voltage. This is somewhat nice in the sense that you can have some more voltage intolerance between devices. You can have higher voltage devices talking to lower voltage devices if they're designed properly, but the other method you wouldn't be able to. But generally speaking, those are two symmetrical systems. One of the tricks here is that clock edges happen in a weird way. Normally we used to think about, okay, a clock edge happens here, and then it transitions, and then it comes back down, and the clock, say a clock edge is here. The clock edge happens in the middle of the bit, and then there's a transition here. Both the rising and falling edge of the clock happen inside the bit, which is just kind of a weird protocol, but because it's as this RC charge up, you can't really rely on the speed up here. So they just make it happen really fast, happen right inside the data. So it's a slightly different clocking scheme. There's a start condition here where data has to be pulled down. Then it checks to make sure that it actually got pulled down. Then clock comes in here and starts its task. Clock ends by going high, and then data ends by going high. That's the stop condition. And here's just an example of this RC charge up issue that you have. This is kind of a poorly behaving S2C bus. One way to make these things sharper would be, how would you make these transitions sharper? What would you do?
Smaller resistor.
Yep, smaller resistor will be able to pull this up. We'll use more current to pull this thing up high, getting over the capacitance on the line, making these edges sharper. And then you get these little runts here can occur. This didn't go all the way up, which could have caused a problem. And so you'd want to go increase your, or decrease your resistance size to increase the current.
You always want to finish like your right read with a knack. Big difference in using like in college versus like inverted.
So, okay, so the question was about a knack versus a knack. So here we have, here it would be a controller talking to a peripheral and saying, hey, is there a peripheral at this address? That's what this packet is. Who sends the ACK bit? What's that? Anybody? Yeah. The peripheral sends the ACK bit. It's basically saying, the controller says, here's a 7-bit address, I want to write to it. Then it says, okay, is that thing on this bus? And if it is, it will ACK. It will pull this thing low. So now we have bidirectional communication here, which is kind of inside the packet. And now the controller says, okay, this thing's actually on the bus, fantastic. Then it goes and sends the data, and it acts again and says, I got the data. And then what do we have here? We're going to say back to that same device, I want to read data out. So this was probably a write bit where it said, give me a certain amount of data. I don't know why it would send all zeros. I don't read the data sheet. I don't know anything. But then it says back to this device, and then the device sends some data back. So here's the device sending back data. And I'm not sure why it has a knack. We'd have to go read the data sheet to figure out. But then there's a stop condition. Maybe it's that the controller says, I'm done communicating with you. That might be the condition. There's no reason to be prepared for the next interaction.
A data sheet whether or not you have your I2C system in with an ACK or an ACK.
The mean, no matter what, I2C has ACKs and NACKs. It's just what is the meaning of the ACK or NACK? That's the question, and you'd have to read your data sheet for it. The one that's the most common is you're writing this address and you want to know, is there a device here? Well, the device has to ACK. If it NACKs, then it might not be on there, maybe stalled, it may be doing another task, it may not be able to respond, or it just might not be soldered onto your device. So a NAC doesn't mean your thing's there necessarily. A NAC, in this particular case, an ACK means the thing's here. A NAC could mean that it's off or just not on the device at all. Yeah.
The NAC and ACK bit being the same like location, would it cause an issue if the ACK, if something that would have caused the ACK to go high happens in the middle of the writing transfer and it wouldn't have been able to finish? Like, would that cause an issue?
If the ACK happens in a bad spot?
Like since the ACK is like saying the peripheral's having a problem, the peripheral has a problem, but the controller.
No, sorry. The ACK means that the peripheral is on the bus and ready to receive. So it means it's good. A NAC means bad, but.
Well, for the STM32, the NAC means that it's done, like transmitting.
Yes, that's why I believe.
So like, what if it had a problem in the middle of transmitting and no longer is able to transmit?
Yeah.
Would that just be lost?
Oh. Yeah, I suppose you've done non-standard protocol things by, I don't know, dying. And so I don't know what happens then. Okay. Probably what's going to happen is nothing's going to be in charge of the bus. I'm just going to guess. And then hopefully, as the microcontroller fails, it just releases these lines and the bus kind of figures it out. Yeah.
Why is there a period where it stops between sending the address and the data?
Here? Or here?
Yeah, why is there a time? Why doesn't it just send the data right after the address? Is there a reason for that?
I don't know specifically what the reason is. The protocol demands that there's some period of time that occurs. How long it is, I don't know. All right, why don't you talk with your neighbor and see if you have any serial communication questions. Oh wait, we don't have any time. Don't talk to anyone. Stop talking. All right, we'll talk about ADCs very quickly. We just did them too. All right, so it's important to remember the basic architectures of your different ADCs. I do not expect you to be able to draw them from memory. I don't know how that would help you as an engineer. But you should be able to look at that and kind of reason yourself through what is the pros and cons of them, or at least to remember, hey, look, this is a 4-bit, or this is a 3-bit? Yeah, it's a 3-bit. I forgot because that wasn't there. 3-bit flash ADC. This is slope integrator, has no resistors. This is that SAR ADC, it has a DAC in it. This is a sample and hold circuit. So you should be able to remember the trade-offs between them. That's an important piece. You need to be able to think yourself through this ladder. So normally we showed it just in this quadrant, but certainly if you had negative voltage, your reference was negative voltage, you could slide this here, you can put it here, doesn't really matter. But here we're just showing this count output and the number of steps, and thinking through how to construct this ladder is an important way to think through both DACs and ADCs. And here we see that this is the minimum step size that can occur, and that relates to a certain voltage range. So I can't measure things smaller than this. So this would be the ADC resolution or the lowest significant bit size for your device. You have a question? No. Thinking through of how the ends of these things work. So this is your VREF negative. This is your VREF positive. Have that, there we go. Typically VREF negative has been shown in most things just to be 0 volts. It makes it easy. That's how most microcontrollers work. However, you certainly will find external ADC modules that you can buy that you could give a negative voltage to, which could be a nice advantage if you're making an embedded system that has to go and measure something from positive to negative rails, and then it will just give you back data. Obviously, that data will be between 3.3 volts and 0, but now your microcontroller doesn't have to have a negative rail, but this external ADC would. So that would be a way to get around that measurement problem. We talked about 4 types of DACs. This is the very simple one, which is this PWM plus a low-pass filter. It's cheap and easy. Basically, you just need to have an op-amp on the output. Your microcontrollers actually have op-amps built into them, the big beefy ones that you guys use in lab. And so you could route it to an op-amp and make sure that you could route it out back into an op-amp and make sure that this thing is well buffered to drive a load. Or it might just be easier just to put an op-amp on your device. You have the voltage divider DACs, which is the inverse of flash. Then there's the 2 resistor network types. The big trade-off between these is how the ratio of these resistors. So this is easier to manufacture. However, it takes more resistors than this one. This is harder to manufacture on chips. So the trade-off here is limited a number of bits, higher number of bits, but harder to manufacture. So just knowing those general trade-offs. And then DACs have the same thing where you have reference voltages for high and low reference voltages. So we have a couple minutes left. Why don't you talk with your neighbors, come up with some good questions about things you are confused about or don't understand about DACs and ADCs. Both of you are my special students here. What questions do you have? I've got to do the I'm sorry? Huh? I can't hear. The second ADC?
Much of a difference at all.
Oh, the slope integrated, yes, constant current source. Oh, these guys are done? What? All right. Yeah. Any last questions? One question, I'll let you all go. Not him, he always asks questions. Somebody ask me a question. Yes.
How's your day?
It's been okay. I'm feeling a little under the weather. All right, see you guys.